We are now ready to undertake a brief but very useful analysis of local maxima and minima for function of the type z equals f of xy. We will extend the second derivative test developed for the functions of a single independent variable. We assume that all second order partial derivatives exist for the function f in some circular region in the xy plane. This is technical details actually for you. This guarantees that surface z equals f of xy has no sharp points, breaks or ruptures. In other words, we are dealing only with the smooth surfaces with no edges, like the edge of a box, breaks like an earthquake fault, or sharp point like the bottom point of the golf tee. Okay, so this is smooth curve. We can discuss the partial derivatives for this function. So this will be absolute maximum, you will see. But this is not smooth. There is a edge. Okay, so this is not smooth curve. This is not also smooth because there is a breaks like an earthquake fault, or this is not smooth surface since it has sharp point here, like the bottom point of the golf tee. Okay, so in addition, we will not concern ourselves with boundary point or absolute maximum minima theory. Despite these restrictions, the procedure we will describe will help us solve a large number of useful problems. What does it mean? For f of ab to be a local maximum or local minimum, we say that f of ab is a local maximum if there exists a circular region in the domain of f with ab as centered such that f of ab bigger than f of xy. Let's interpret this result. Sorry. Here, AB is this point, for example. This is x-axis, this is y-axis, this is z-axis. So this point is A, this point is B. So here, this point is Z, which is f of AB. Okay. So this is a local maximum value. This is the Z equals f of AB value. So let's write it as a point that this one. So this is the point A, B, and Z. Z is f of A, B. Okay. So here, for any circular region, let's look to here. For example, this circular region. By choosing any point at that circle, okay, you can see that this is the f of xy value for this point, okay. So this is less than the f of ab. So f of ab bigger and equal f of xy for all x in this circle, okay, in circular region. Or it can be minimum value. Let's show that some other figures to you. Here, okay, Same situation as it can be observed from here. F of AB bigger and equal f of xy for this circular region. This is your point xy, for example. Okay, so this value is less than the, actually this value is f of xy value less than the f of AB value. Here, for this circular region, for example, we have this circular region. So your point xy is here. So the function of f of xy value at that point. So this is f of xy, and for the a, this is f of ab. As you see, f of ab less than equal f of xy for all xy in this circle. Here you can choose the another point. Again, this is bigger than the f of ab, etc. So this is local minimum. And here let's look in the figure C. Among this line, we have this graph. So we have a local maximum. But along to this line, we have this curve. So this is local minimum. So in that situation, this point is called a saddle point, okay? So saddle point is neither a local maximum nor a local minimum. So what happens to a partial derivative of f with respect to x and partial derivative of f with respect to y if f of function f is a local minimum or local maximum and the partial derivative of f exists in a circular region, okay, containing AB? This is the important question. Actually, along to that part, actually let's turn back to this part. So along to this line, we have this curve. So it is stationary. So it increase. At that point, it stop and start to decrease, okay? And similarly, along to this line, this is our curve. So it is increase, starts to decrease. So again, it's stop at that point. So this is a stationary point. So like the one variable case, the blue curve represents the change of the x, so partial derivative of the f with respect to x. So here, this line says partial derivative of the x is 0. This line says partial derivative of the y is 0. Okay, and similarly, here the partial derivative of the y is 0. Here the partial derivative of x is 0. And here along the blue curve, this is local maximum. But anyway, partial derivative of the f with respect to x is 0. Along the red line, or this part when y change but x is constant, we have the red curve. The red curve has local minimum, so it has again it says partial derivative of the f is 0. So as a result, we can say that let f of AB be a local extremum, either local maximum or local minimum for the function f. For the saddle point, it's also valid, okay? And if both partial derivative of f exist at the point AB, then partial derivatives are 0 at the point AB is 0, and partial derivative at the point AB is 0. But like the first one variable functions, the inverse of the converse of this theorem is not correct, okay? I mean, if the all partial derivative are 0, it may not local maximum or local minimum. Okay, it can be saddle point, as you see from here. In the one variable case, it can be inflection point, okay? For example, consider the x cube. First derivative of the x cube is 3x squared. So for x equals 0, 3x squared is 0. This is the critical point, but there is no local minimum or local maximum, okay? So saddle point like a stationary point, but of course we have a surface, so it is a completely different concept. So in light of this fact, if at any point AB all partial derivatives are 0, these points are candidate being a local minimum or local maximum. So these are critical points for us, okay? So if all partial derivative at the point AB, if you have three variables, you can get the three variable are 0. This implies AB is a critical point. Critical point. How we can decide this critical point, either local minimum, local maximum, or saddle point? According to the following theorems, we can decide. So this next theorem, this theorem, using second partial derivatives, okay, give us the sufficient conditions for a local point, for a critical point to produce a local extremum or a saddle point. So if z is the two variable function in terms of x and y, and all partial derivative f with respect to x and derivative of the f with respect to x and with respect to y are 0, that means AB is a critical point. Also in all second order partial derivative of f exists in some circular region containing AB. AB is the center, of course. And you can calculate these two values if this is all second order partial derivative exist. So let's say this is A, partial derivative of the f with respect to x and x is A at the point AB. Partial derivative of the f with respect to x and then with respect to y at the point AB is B, capital B, and that is C. So according to this A, B, C values, okay, actually that is equal for second one, this equals f sub yx, okay, AB. So then if AC minus B squared bigger than 0, it is like the second derivative being a positive second derivative value. I mean, for example, let's recall single variable function. What is the second derivative of this function? The first derivative 2x, second derivative is 2. So 2 is positive. So here we have a local minimum or absolute minimum here, but in general local minimum. If second derivative is positive, we have a local minimum. So here, if second derivative is positive, A represents the second derivative fxx, okay? So this is local minimum. If a second derivative, but we have several second derivative, of course, but this represents this case, okay? So to recall easily, I try to explain. There is a local maximum, or f of AB is a local maximum value. But since we have two variables, we should check the AC minus B squared under this assumption. AC minus B squared bigger than 0, and if A is less than 0, local maximum. If A is bigger than 0, local minimum. If AC minus B squared less than 0, in that case, f has a saddle point at the point AB. If AC minus B squared is 0, the second derivative test fails, okay? you cannot use the second derivative test. In such case, we analyze by using different strategies, but in this course, we will not discuss that strategy.